Okay, so let's quickly review what we did in the last lecture. So we started with the iterative methods for solving the linear systems. And the first method which we saw is the Gauss-Jacobi method, which we simply call the Jacobi method as well. So what do we do in this Gauss-Jacobi method? So suppose we have to solve the linear system, which is of form Ax is equal to B, right? So A is the matrix with the coefficients A11, A12 up to A1n. Let me write it in the, oh, sorry, let's write it in the full form. With the last row as this, right? And X is a vector of length n with the components x size, and B is also a vector of the same size as X with the component as Bi. Okay, so this is n by n matrix. So what was the idea of this Gauss-Jacobi method? That we rewrite this linear system. So we can rewrite one as x is equal to bx plus c with this new matrices B and C as. So B is the matrix with the entries as, so the first row is minus A12, A11 up to minus A1n divided by A11. Second row, we will have the first entry as this, and the diagonal is basically 0. And the last row is going to be an1 divided by ann minus an2 divided by ann, and the last entry is going to be 0. And C is the vector b1 divided by a11, b2 divided by a22, and the last entry is bn divided by an. So basically, we just solved for the, say from the first equation we solved for x1, from the second equation we solved for x2, and like that, right? So then in the left hand side we will get the vector x, and we wrote the right hand side in this form. Okay, so we used this equation to design this Jacobi method. So what is the iterative sequence we get using this equation to? That if we want, knowing the initial guess, say, so if initial guess is x1, which is nothing but the vector with the component x1 up x2 up to xn with the superscript 1, then I can generate the sequence of iterates, say k plus 1th iterate. This is given by b times x, the kth iterate, plus c. Okay, so it depends what your, yeah, so k is, I'm having x1, so k is going to be greater than equal to 0. Or in, if I want to write it in the component form, so xith component of this k plus 1th iterate is going to be, so I'm just simplifying this multiplication b times x plus c. So this is going to be bi minus summation aij xj from the kth iterate, and j is ranging from 1 to n, and j is not equal to I, and everything divided by aii, right? And this is for each I. Okay, so this is the Gauss-Jacobi method, or simply the Jacobi method. All right, so you start with the x1 and then you can use x1 to generate x2 and then use x2 to generate x3, and like that you can generate this iterative sequence. Now, where do you want to stop? This just depends how much accuracy you want. So you can check the, we have in the starting, that is when we were learning the methods, root finding methods, then we have learned that how to set the stopping criteria, right? You can check the relative error or absolute error or the combination of both. And when this relative error is less than the given tolerance, that is epsilon is given by the user. Say, if I'm giving you that, okay, I want the solution difference, that is a relative error, should be less than equal to 10 to the power minus 6, right? So you can stop according to that. When you reach, you just compute the relative error, that is you compute xk plus 1 minus xk divided by, so you have to take a suitable norm, xk plus 1. And when this is less than epsilon, you can stop the algorithm. Okay, so any of the stopping criteria you can use to stop the iterative, like this k till where you have to go. This will be just depending on what is the accuracy you are seeking. Okay, and then we also obtain that how the error behaves for this method. So if we call it 3. So we obtain that if A is a diagonally dominant matrix, that is, I have that if I sum all the non-diagonal entries, from the, say, ith row, so this is going to be less than equal to absolute value of aii, and this holds for each I. Okay, then we had defined this parameter mu, which was nothing but, so I sum it over all the j's. J is not equal to I, the ratio aij divided by aii, and I take the maximum over all the i's. Right, so this is nothing but the row norm of this matrix B, right? So if matrix A is diagonally dominant, then this is going to be strictly less than 1, and we obtain that the error to be denoted it by, I think, ek. So this behaves like mu raised to power k times e0. Right, so ek is nothing but x minus the kth iterator x. Right, so this means that the error converges linearly with mu as the rate of convergence, right? And mu is here this, which is strictly less than 1. So that ensures that the error is going to go to 0, right? So we can conclude from here that ek goes to 0 as k tends to infinity. So then we also saw the Gauss-Seidel method, which was a modification of this Gauss-Jacobi method. So what was the modification here? So let's write down what the method we have in the Gauss-Jacobi. So here we have that k plus 1th iterate of, so ith component of the k plus 1th iterate is given by 1 divided by aii bi minus summation j equals 1 to n, j is not equal to I, aij, and jth component of the kth iterate. So this is what we have from the Gauss-Jacobi method, right? So let me just break this sum in 2 parts. So I'm having j is equal to 1 to n. Okay, so I'm going to break it up to the indices. So I'm writing the ith component. So I'll break it into the up to the I minus 1 and then from I plus 1 because j is equal to I is anyways not here, right? So I can write this sum as j equal to 1 to I minus 1 and then j is equal to I plus 1 to n. So this is what the Jacobi method is, right? Now, what is the difference in the Jacobi and Seidel? So if we are finding the ith iterate, ith component of the k plus 1th iterate, this means that I have already computed first, second up to the I minus 1th iterate of the k plus 1th iterate, right? So I'm going to use that to compute the ith iterate. That is, I'm using the information which I have already got for the k plus 1th iterate to find the ith component. So I already have x1, x2 up to xi minus 1 for the k plus 1th iterate. So that I use to compute the ith component of the k plus 1th iterate. So this is what the Gauss-Seidel method is. So if I number this, so this is 4. And now what we want to understand. Okay, so here this is for each I. Okay, so now we want to understand that how the error behaves for the Gauss-Seidel method. So let's denote the error by ek again. So ek is x minus xk. Okay, so my k plus 1th iterate is given by this equation 4 for the Gauss-Seidel method. And note that my solution is still satisfies the same system, right? I can write my solution in this form, which is given by 2. X is equal to bx plus c, right? So which means that my x exact solution is satisfied. The ith component of the exact solution is 1 divided by aii bi minus summation j equals 1 to n. J is not equal to I aij xj, and this is for each I ranging from 1 to n. Okay, and we have the approximation of this xi is given by 4 for the Seidel method. So what I'm going to do, I'm going to simply subtract these two equations. So if I name this 5, so subtracting equations 4 and 5. So that will give us that. So if I subtract the left hand side, you see that I get the error at the k plus 1th iterate, right? So this is going to be the error for the k plus 1th iterate and ith component of that, right? So when I write this ek as this, so this is also a vector because x and xk both are the vector. Okay, so ei is going to be basically this will also have the n components. Okay, so when we subtract 4 and 5 in the left hand side, we are going to get the ith component of the k plus 1th iterate for the error e. Okay, and in the right hand side, you can observe that this term is the same in both, right? So this term will cancel out. And this here, this sum, I can again break it in two parts. So I'll write this as j is equal to 1 to I minus 1, and then j is equal to I plus 1 to n. Okay, so that I can club the terms here. So what I will get upon simplifying that, this is going to be j is equal to 1 to I minus 1 aij divided by aii, and I will get, so when I will subtract the components here, so I'm going to get the jth component of the k plus 1th iterate with a minus sign, and j is equal to I plus 1 to n. I'm going to get aij divided by aii and jth component of the kth iterate. So you agree with this? So this is, I'm simply subtracting them, and this is what we get. So now we have already introduced this parameter mu, right? So what is mu? In the Gauss-Jacobi method, we introduced this one, right? This was a row norm of the matrix B. So here we are getting, if you observe, we are getting these components, but the summation is from j is equal to I minus 1 here, and then this is from I plus 1 to n. So let me introduce the new indices here. So I'm defining, so let me use some notation. So I want to define this factor aij divided by aii with the sum from j is equal to 1 to I minus 1. So we are going to call this as alpha I. And then let's consider the sum from j is equal to I plus 1 to n aij divided by aii. So let's call this as beta I, because note that we have a sum over j's, right? So it is still depends on the I. So this is for each I equal to 1 to up to n. But if you note that if we take I is equal to 1, right? So this is simply 0. So alpha 1 is simply 0. And likewise, beta n is 0. Okay? Because note that beta n is not defined by this, right? So I'm simply setting beta n to be 0. So then if I observe the mu, which is nothing but maximum over all the i's, summation over all the j's of the factor aij divided by aii. So this I can simply write it as, so this factor is simply the sum of alpha I and the beta I, and here I have the maximum over all the i's. Okay. So let's give it equation number. So this is 6. And now for this method also, I'm going to assume that the matrix is diagonally dominant. That is, in a way, I'm going to assume that mu is strictly less than 1. Okay. So now let's go back to this error equation. Okay, let's name this as 6 and this as 7. So now let's look back this error equation 6 again. So from 6, so I'm just going to take the absolute value both sides. So we're going to have that absolute value of ith component of k plus 1th iterate. This is less than equal to. So note that when I take the absolute value, I can use this notations alpha I and beta I. So what I will get from here? So let's write it down. First, I'm going to get that summation j equals 1 to I minus 1, absolute value of aij divided by aii. And then we have absolute value of jth component of the k plus 1th iterate. And then we are having j is equal to I plus 1 to n, absolute value of this factor times ejk. Okay. So this term, this is less than equal to the L-infinity norm of the error at the k plus 1th iterate, right? Because this is nothing but the maximum of all the eases, where j is ranging from 1 to n, right? Likewise, this factor here, this is less than equal to the L-infinity norm of ek, right? So, and whatever is the remaining thing, you can see that this is going to be alpha I, and here we are going to get the beta I. So this is less than equal to alpha I times L-infinity norm of ek plus 1 plus beta I times L-infinity norm of ek. Okay, and this still remains true for each I. All right. So it's still here in the left hand side, I'm still having the ith component of the error, right? So what I aim to bound, I aim to bound the that I should have something that error in the k plus 1th iterate is less than equal to some factor times error in the, so it should be in one previous step, right? So this is something what I'm aiming for. So still I have ek plus 1 L-infinity norm present here, but in the left hand side I have the ith component of this. So what I'll do, if you look at the this error, so what is this? This is nothing but the maximum of absolute value of is, that is the error in the jth component of the k plus 1th iterate, and j is ranging from 1 to n. Okay. Now this maximum will be attained at one of the indices, right? For one of the j, value of the j, you will get that the error is maximum. Say at the mth component, the error is maximum, right? So let's call this as em k plus 1, right? That is what we are having. Let m be the subscript for which I have that the error in the k plus 1th iterate is attained at the mth component. Okay. So now this result, that is this equation, let's name it the equation number 8. This holds for each I, right? So in particular, it will hold for I is equal to m. So what we'll get? We'll get the m component, mth component of the k plus 1th iterate. This is less than equal to alpha m, L-infinity norm of the error in the k plus 1th iterate, plus beta m times ek L-infinity norm. Right? Now this is nothing but the L-infinity norm of the error ek plus 1, right? So now I can combine these two terms. So I have this term here, and the same term is sitting here. So I'll bring this term from the right hand side to the left hand side, and I'm going to get that 1 minus alpha m times L-infinity norm of the ek plus 1. This is less than equal to beta m times L-infinity norm of the ek. Or I can simply take this factor here, 1 minus alpha m. Okay, and note that 1 minus alpha m is not equal to 0. Why? because alpha m is going to be strictly less than mu, and mu is strictly less than 1. Okay, so the denominator is not equal to 0, so I can divide by 1 minus alpha m here. All right, so now we have got this factor here. So let's do a further simplification here. So if I take the maximum of all these factors, that is, I'm taking the maximum about all the i's, and let's call it to some parameter. Let's define it by eta. Okay. So then I can write down that this is less than equal to eta times L infinity norm of the ek, where eta is defined by this. Okay, so we have got this relation. So let's number it. So this is 9. So you can, if you just try to compare it with the Gauss-Jacobi method, we got a similar equation there, but instead of the eta, we had a mu there, right? So now I'm claiming that my convergence is going to be faster in the sense that this parameter is going to be small, right? So let's see whether this is actually smaller than mu or not. So for that, what I have to do, I'm simply going to consider. So I know that mu is maximum of alpha I plus beta I, right? And here eta is the maximum of this ratio. So let's consider this difference. So let's take alpha I plus beta I. And here we have beta I divided by 1 minus alpha I. Right? So let's consider this difference for each I. Let's simplify this. So if we just multiply here, so we will get alpha I plus beta I minus alpha I plus beta I minus beta I divided by 1 minus alpha I. So if I take out the, so beta I gets cancelled here, and let me take out the factor alpha I from here. So I'll get 1 minus alpha I plus beta I divided by 1 minus alpha I. Okay. Now further, what can we do here? So I want to bring mu into the picture here. So what should we do? So we have this factor alpha I divided by 1 minus alpha I here, and we have 1 minus alpha I plus beta I. So we want to prove that this is greater than equal to 0. So can we say that? Okay, so let's pay attention to this factor. So mu is nothing but, just recall, mu is nothing but maximum of alpha I plus beta I for each I. Right? So what we have, that mu is strictly less than 1. Right? So if mu is strictly less than 1, this means that alpha I plus beta I for each I, that is also going to be strictly less than 1. Okay, so this means that this factor here is positive, and you can observe that alpha is also strictly less than 1. So this factor is also positive. So this means that overall this is going to be greater than equal to 0 since we have this. Okay. So what we have got out of this? So this will imply that this is the maximum of this is mu and the maximum of this of eta. So basically I have that eta is mu minus eta is greater than equal to 0. This means that eta is less than equal to mu and mu is strictly less than 1. Okay, so we have two conclusions from here that eta is also strictly less than 1 and eta is also less than equal to mu. Okay, so if I look back the equation number 9, so from here, if I iterate this process here, that is ek will be less than equal to eta times ek minus 1, and further ek minus 1 will be less than equal to eta times ek minus 2, and likewise. So I can write down that ek is going to be less than equal to eta raised to power k times E0. Right? So eta is strictly less than 1. So this means that ek goes to 0 as k tends to infinity. And what about the convergence? The convergence is linear because you can see that the relation between the ek plus 1 and the ek. So this is a linear relation and the rate of convergence is eta. So see, in terms of the order of the convergence, Jacobi method and the Seidel method, they both converge with the linearly. But what is difference here? That you get a component eta, which is less than equal to mu. So basically, you are getting a faster convergence, rate of convergence in that sense. So the convergence is linear, but with a faster rate than the Jacobi method. Okay. So are there any questions here? All right. So note that here we have discussed two methods, Gauss-Jacobi and the Gauss-Seidel method, but there are other iterative methods as well. So I'm not going to go into the details of for each of the method, but rather I'll give you a general framework that how does we design these iterative methods for any, like, any general method. If you will see, they all will be falling in this general framework. So let's discuss that what is a general framework to design the iterative methods. So what we are interested, we want to solve the linear system Ax is equal to B. Okay. So here, what we are going to do, we are going to split the matrix A as n minus P. Now we'll see in a minute that how we have to design n and p here. Okay, because based on how you design n and p, you're going to get a numerical method. So suppose I could find n and p so that n and p are such that n minus p is a. Okay, so ultimately we are interested in solving nx is equal to b, which will be giving us that I'm having the equivalent system as nx is equal to b plus px. Okay, so this gives the idea that how I should choose my n. So we know that we have seen that there are certain structure of the matrices for which we can easily solve the linear systems, right? That is, if we have, say, diagonal matrices or the tri-diagonal matrices or the triangular matrices, for these kind of matrices, we can easily solve the linear systems. So I'm going to choose my n such that the system, if we consider, suppose, take any right-hand side vector, say f, and we have to solve, say, nz is equal to f, so this should be easily solvable. So that is my first criteria to choose the n. So let's write it down. The matrix n is chosen such that the linear system, that is, if I have n as the coefficient matrix for any linear system, say if we have given right hand side vector as f, and I want to solve nz is equal to f. So this would be easily solvable. Okay. So for example, we have seen that, let's say if n is, it can be a diagonal matrix, or it can be a tri-diagonal, or it can be a triangular matrix, upper triangular or the lower triangular. Okay, because we know that for these kind of structures on the n, I will be able to solve the system easily. Now, once we have chosen the matrix n, I can define the numerical method as note that once we have found n, right, you have designed what n you are requiring, p is simply going to be n minus a. Okay, so having chosen n, we can write down the iteration method. So I'm going to use this equation to design the iteration method. So knowing the xk, the kth iterate, I want to find the k plus 1th iterate. So I'm going to find the k plus 1th iterate by this equation. Okay, and here the initial guess is going to be, so I'm writing k greater than equal to 0. So x0 is the initial guess. Okay, which means that this is a given vector. So example of this particular setting, we have already seen the Jacobi method, for example. So what is the matrix n for the Jacobi method? Can you tell me, please? Any of you? Okay, if you just try to see how I obtain the form of the Jacobi method, so n is nothing but a diagonal matrix with the entries, with the diagonal entries are aii. Right? So you just try to pay attention what we have here. So how we are obtaining the system? We are just solving, we divided by, so for example, if you look at the first equation, we have a11 x1 plus a12 x2 up to a1n xn. This is equal to bn, right? So from here, I solved for the x1. So a11 x1 is bn minus a12 x2 up to minus a1n xn. Likewise, you will be solving for x2, x3 up to xn from each of the equation. That is, from the second equation, you will be solving for x2. And in general, from the ith equation, you will be solving for xi. So you will get here A11 here. If I do not divide by A11, then I'll be having the A11 sitting here. In the next equation, I will get A22 times X2 likewise, right? So this is nothing but if you try to write down this in the matrix form, this is going to be n times x, where n is nothing but a diagonal matrix with the diagonal entries as aii. Okay. So once you have found what is n, then p is simply going to be n minus a, and then we can design the method by this equation. Okay. So n of the iterative method is given by n of xk plus 1 is b plus p times xk. Okay. And if you try to observe for the Gauss-Seidel method, what is the matrix n? So you have to observe what is getting multiplied with the k plus 1th iterate, right? So if you try to, okay, this is for you to check that n for the Gauss-Seidel method is nothing but a lower triangular matrix. So if I take the lower triangular matrix, lower triangular part of the matrix A, that is I'm going to take the diagonal, below diagonal part. So A11, A21, A22. The last row is going to be AN1, AN2 up to AN. And all the entries above the diagonal is 0. Okay, so which is a lower triangular matrix. So we have n as this, and p you can find it by subtracting a from n. Okay, and you try to write down what this equation is giving to you. This is the same as the iterative methods. Let's give it a equation number. So this is, let's call this as 10, 11, and 12. So let's try to see that how the error behaves for this general setting. So if I just subtract the equation number 11 and 12, this is the error analysis. So from equation 11 and 12, so I can write down. So if I use the same notation, ek for x minus xk, then I can write down that n times ek plus 1, this is going to be, b is going to be the same in both the equations, so b will cancel out. So I will get this as p times ek. Okay, or I can write down that ek plus 1. So another requirement I can see on n, that n has to be an invertible matrix. So I can write down this in this form, where m is nothing but n inverse p. Okay, so from here I can obtain that the norm of the error in the k plus 1th iterate, this is less than equal to norm of m times the norm of the error in the kth iterate. Okay, and if you just repeat this process, that is, you just recursively, if you just bound this by, so this is going to be less than equal to m times norm of ek minus 1, and if you repeat this, we will get that that the norm of the Ek is less than equal to norm of m raised to power k times norm of E0. Okay, so what is the criteria for the convergence of this Ek? So I have to have that norm of m has to be strictly less than 1. Okay, so now with this I can summarize that what all the requirements I want on the matrices N and P. So we're going to find the matrices N and P such that we are going to have that the norm of matrix M, which is nothing but the N inverse P, this is strictly less than 1. Okay, while also having that the system Nz is equal to F, this is easily solvable. Okay, and another thing you can notice here is that the convergence is this is not depending on the initial guess. You choose whatever is the initial guess. If you have that the norm of m is strictly less than 1, then the iterative sequence which you are going to construct using this method, that is going to go to the exact solution. That is, the error is going to go to the 0. So the convergence is not depending on the initial choice. So note that the iteration method converges for any choice of the initial guess x2. Okay. So are there any doubts so far? Okay, let's take some problems and try to solve them. So we have learned the Gauss-Jacobi and the Gauss-Seidel, right? So let's solve some problems. Suppose we have to find the solution of this linear system 2x1 plus x2 plus x3, this equals 5, 3x1 plus 5x2 plus 2x3, this equals 15, and third equation is 2x1 plus x2 plus 4x3, this equals 8. Okay, so for understanding purpose, 3 by 3 system suffice. So we're just going to solve it using the Gauss-Jacobi method. And the initial guess is, let's take the initial guess to be. So this is given to be, I think we used x1 for the initial guess there. So let's write down x1. So this is with these 3 components. So this is 0 vector. Okay. So for the guessed Jacobi method, what do? We simply solve for the xi from the ith equation, right? That is, I'm going to solve for x1 from the first equation, for x2 from the second equation, and for x3 from the third equation. Right? So if I number this as 1, this as 2, and this is 3. So then we are going to solve for xk in terms of, so k is 1, 2, 3 here, in terms of other unknowns. From equation which is numbered as k, and k is 1, 2, 3. Okay, so this is why I'm just writing all this thing. I could have directly, we have a formula and I can directly use that, right? But see, I don't want to remember the formula. I just want to understand, if I have understood what I am supposed to do, what this method does, I don't have to remember the formula of these methods, right? So I just solve for x1 from the first equation. So I get x1 as 1 by 2, 5 minus x2 minus x3, and x2 from the second equation. So this will give us 1 by 3, no, 1 by 5, 15 minus 3x1 minus 2x3, and x3 from the third equation. So this is going to give us 1 by 4, 8 minus 2x1 minus x2. Now I can easily write down the iteration for the Gauss-Jacobi method, right? So the iterative sequence. So let's write down the general iteration k plus 1. So this is going to be 1 by 2, 5 minus x2 from the kth iteration minus x3 from the kth iteration. Right, in x2 for k plus 1th iteration is 1 by 5, 15 minus 3 times x1 from the kth iteration minus 2 x3 from the kth iteration. And x3 for k plus 1th iteration is 1 by 4 times 8 minus 2 x1. X1 is from the kth iterate and x2 is also from the kth iterate. And k here is, so I'm starting from the 0. So it is going to be 0, 1, 2. Sorry, I'm starting from 1. I'm setting 1 as the initial guess. So this will be from 1. Because you can see here in the right hand side, we have xik, right? So I have set the first iteration as the initial guess. So I'm starting from 1. So let's compute 1 or 2 iteration and then you can complete this exercise. So in particular, for k is equal to 1, that is the first iteration. So I'm going to get x1, 2 as 1 by 2, 5 minus x2, 1 minus x3, 1. And I know that x2 and x3 both are 0, right? Because 0 is the initial guess. So this is going to be 5 by 2, which is 2.5. And x2, 2 is going to be 1 by 5. And x1 and x3, they are also 0. So I'm going to get 15 here. So this is going to be 3. And x3, 2 is going to be, so x1 and x2, when k is equal to 1, they are 0. So I'm going to get 1 by 4 times 8. So this is 2. Okay, now you can just repeat this process, right? We have found x1, that is our first iteration, we have found it. So now you can find the second iteration. So x1, 3, this is going to be, so again, I'm going to use the same equation. So this is 1 by 2, 5 minus x2, 2. x2, 2 is 3. and x3 2. So this is 2. So this is going to be 0. And x2 3, this is going to be 1 by 5 times 15 minus x1 2, I have computed to be 2.5. So 3 into 2.5 minus 2 into 2. So this is going to be, so you can simplify this, 5 by 2 into 3, 15 by 2 and 15 by 2 minus 4. So you can simplify this, what you get as an output. Okay. And x3 3 is going to be 1 by 4, 8 minus 2 times 2.5 minus 3. Excuse me. So this is 5 minus 3, so this is 0. Okay, and likewise you can continue up to the desired, you get the desired accuracy, right? You will be finding the, say you can compute the third iteration. So this you can write it down, what the output you're going to get, and you can continue the process. Till the desired level of accuracy is achieved. Okay, so when I say desired level of accuracy, that is you have to find the relative error at each iteration level, and that has to be less than equal to given epsilon. So this is a given by user. Okay, so mostly you will be like, these algorithms are used in the computer. So by hand, of course, it is, so for 3x3 system, it is still easy, but if you have a larger system, you cannot do it by hand. So these algorithms are designed to use in the computer. Okay, but for 3x3 system, you can do it by hand itself. So now let's take one example for Gauss-Seidel method. So I think we can solve the same system. So we have this system. So now let's solve it by Gauss-Seidel method. So let's solve it using Gauss-Seidel method. So again, I have solved for the diagonal elements. So these x1, x2, x3, I already have it. So x1 is 1 by 2, 1 by 2, 5 minus x2 minus x3. And x2 is 1 by 5, 15 minus 3x1 minus 2x3. And x3 is 1 by 4, 8 minus 2x1 minus x2. Okay, and initial guess is 0. So let's take x1 0 is 0. Sorry, x1 we are setting it with the 1. So x2 1 is 0 and x3 1 is 0. So how we set the iteration for the Gauss-Seidel? So again, I'm going to see these equations. So I'm going to find the first component of the k plus 1th iterate. So this is going to be, so note that when I'm computing the first iterate, I do not have any information about the k plus 1th iterate, right? So I'm simply going to use the information from the kth iterate, right? But now I have the information for the x1 from the k plus 1th iterate. So that I will use in the x2. So here instead of k, I will use k plus 1. Okay, and x3 I don't know yet, so I will use it from the iteration label k. And now for x3, I have the information for both x1 and x2. So that is what I'm going to use. So 8 minus 2x1 from k plus 1 minus x2 from k plus 1. Okay, so let's generate few iterations and see what do we get as an approximation. So this is iteration 1. So I'm going to get x1 2. So this will be 1 by 2. 5 minus. So this will be the same as before because I'm using the same initial guess. So x2 2 is going to be 1 by 5. 15 minus 3 times. So I'm going to use this 2.5 here, right? So this will change than the previous approximation. Minus 2 into 0. So this is 5. So this is 1.5. And then x3, we can find it. This is 1 by 4. 8 minus 2 into x1, k plus 1. So this is 2.5 minus 1.5. So this is going to be 5, 3 minus 3 by 2. So you can simplify this, what you get here. So we have 8 minus 5 minus 1.5. So this is going to be 3 by 8. Okay, so now you can find other iteration as well. So I'm just leaving this for you to work it out. Okay, and as before, you can stop it when you get the desired accuracy. Okay, so we can continue. Until we get desired accuracy. All right, and this is a 3 by 3 system, so you can find its exact solution as well, and you can compare from that as well, right? That which is giving you the faster convergence. Okay, so you find the exact solution. This you can find it, and then you can compare it with the output what we are getting from these Jacobi and the Seidel method. Okay, so this is how we use these methods to find the iterative sequence. So now, since I have some time, so I'm just going to discuss a few variations of the methods which we have learned. So for example, we have learned the direct methods, Gauss elimination and LU decomposition, right? So there are some variations of those methods which are also used for particular purposes. So let's see, discuss them. So the first method in that direction is Gauss-Jordan method. So this is basically a modification of the Gauss elimination method, right? So if you see in the Gauss elimination method, let me explain it by taking one example. So suppose we have 3 by 3 system. So what do we do in the Gauss elimination? So for example, I'll be starting from this, making this element as a pivot element, right? I just check that this element is non-zero. So with that assumption, I eliminate x1 variable from the second and third equation, right? Now, when I come to the second, in the modified system, we will have zeros here, right? And the element which will be sitting here, that will be my pivot element. And I use that to eliminate x2 from the third equation, and we repeat this process. Okay. Now, how this method differs from the Gauss elimination, that we are not, suppose I'm on the equation, say I'm eliminating x1, okay, or in general, say I'm eliminating xi from the ith, from all the equations I plus 1 to n. So I will not be just eliminating from the equation I plus 1 to n, which is done in the Gauss elimination. Rather, I'll be eliminating from all the equations other than the ith equation. So that's the difference. That is, if I talk about the this component here in the modified system. So in the Gauss elimination, I just use this element to eliminate the this factor, right? You will be having a3, 2, 1 into x2. So you eliminate this component. But in the Gauss-Jordan, you will not be just eliminating this, but you will be eliminating this element as well. That is, you want x0 here as well for the x2. Okay, so let me write it down. So this is a modification of this method is a modification of Gauss-Jordan method, Gauss elimination method. And the difference from Gauss elimination method is that in Gauss elimination, we eliminate the variable from the rows below the pivot equation. But in Gauss-Jordan method, this variable is eliminated from all the rows other than the equation which, so it is eliminated from all other rows. That is not just the rows below, but also from the rows above. Okay. And then finally, you can, if you imagine, you will be having only the diagonal entries in the matrix, final matrix, which you will get as a coefficient matrix, right? So, and finally, what do? We divide by these diagonal elements. Further, all rows are normalized by dividing them by their pivot elements, right? So if I take the again the 3 by 3 matrix, Suppose we are solving this system. So if I apply the Gauss elimination, so what is going to be the output of this system? So in the final matrix is going to be upper triangular matrix, right? So the first row will remain as it is. The second row here it will be 0, and here it will be modified to A22. So sorry, let's use the 1 here and 8231, and then this will be 0 here. This is again going to be 0, and here I will have the modification of this entry, and this equals B1. Sorry, this is B2 1 and B3 2, right? So this is what we get as a result of Gauss elimination. Okay? And if you apply the Gauss-Jordan method, so you can see the matrix, the coefficient matrix, this is going to transform to an identity matrix. So these entries are going to change. So B1, let me use a different notation, B2 double prime and B3 triple prime. Okay, so this is the result of when you apply this procedure of Gauss-Jordan. Right? But mostly this method is not really used for finding the solution of the systems, for the reason that if you count the number of operations, okay, so you just try to count that how many multiplication, subtraction, and division you are performing to finally obtain this system. Okay, so they are going to be approximately n cube by 2. Okay, so these are, if you are performing the Gauss elimination, the number of operations that is approximately n cube divided by 3. Okay, and if you perform the Gauss-Jordan, the number of operations in here that you're going to require is approximately n cube divided by 2. So if your n is very large, so this means that you can see that Gauss-Jordan is going to require more time to get the solution as compared to the Gauss elimination method. So what this method is mainly used for, so if you have to find the inverse of a matrix, okay, so you would have probably used this method that you write down that A into B, this is equal to I, and you apply the row operations. So this becomes I, and this matrix will be transformed to A inverse. Okay, so this Gauss-Jordan method is mostly used to compute the inverse of the matrices rather than solving the systems. Just because we have a more operation counts if you're performing this to solve the system. Okay, so let's quickly discuss one more method. This is the Cholesky method. So this method is a modification of the LU decomposition. So here I'm assuming that the matrix A is symmetric and positive definite. So what's the positive definite matrix? So I hope you guys are familiar that what is a positive definite matrix. Can any of you tell me?
Yes, ma'am. If all eigenvalues are positive.
Yeah, so you can check the eigenvalues, or its definition is that if you compute, you take any vector x, right? And if you compute this product, x transpose ax, this is strictly greater than 0 for all x, which are non-zero. Okay, so if your matrix satisfies this, you say that that is a positive definite matrix. Okay, so if you have a matrix which is a positive definite matrix, and if you're interested, the interest remains the same, that we are interested in solving ax is equal to b. So in the LU decomposition, what we have seen, that we can decompose this matrix A as L into U, right? But the Cholesky method is basically says that if you have a positive definite structure together with the symmetricity, then we can write down A as L into L transpose. That is, the upper triangular matrix here is nothing but the transpose of the lower triangular matrix. Or you can have the representation of A in terms of the upper triangular matrix as U into U transpose. Okay. So let me just mention here, in case A is symmetric, and positive definite, the LU decomposition can be modified so that the upper triangular matrix is the transpose of the lower triangular matrix. Or you can have it vice versa. That is, if you want to write it in terms of the upper triangular matrix, then the lower triangular matrix is going to be the transpose of the upper triangular matrix. That is, I'm going to have the factorization of A as L into L transpose, or you can have A as U into U transpose. Now, how will you find this L and L transpose? It's the same procedure what we have done in the Doolittle factorization, right? So suppose if I'm focusing on this, L is going to be a lower triangular matrix. So you take the L to be L11, 0, 0. I'm just writing it for the 3 by 3 system. So L21, L22, 0, L31, L32, L33, and you simply multiply this with its transpose and you equate it to the A. So you will get a relations between the Lij's and the Ai's. So basically using that, you can compute all these entries Lij's. So I can write down. So upon simplification, we will get the Lij's as, if I write down L as, so simply multiply and equate it to A, we are going to get Lii as Aii minus summation k equals 1 to I minus 1 Lik square and square root of this complete quantity. Okay. And then the other entries can be computed by using these LII. So this is going to be Aij minus summation Lik Ljk k is ranging from 1 to j minus 1 divided by Ljj. Okay, so this you can directly use these formulas to compute the entries of this lower triangular matrix L. So let's take one example and try to solve it. Factorize it using the Cholesky method. So we factorize the matrix A, which is having the first row as 1, 2, 3, second row is 2, 8, 22, and third row is 3, 22, and 82. So L I'm seeking as L1100, L21, L22, L31, L32, and L33, right? And I want to have the Cholesky factorization of A. So this is L into L transpose. So I'm directly going to write down, if you can simply multiply it and equate to A, you will get the same formulas what I've written here. So I'm directly going to use this formula. So if I number it, so let's number it as 1, 2, and 3. So first you can observe that if I have I is equal to 1, then from equation 2, the summation will not be contributing because I'm having k is equal to 1 to I minus 1. So I is 1 here. So this is not contributing. So I have L11 is the same as square root of the A11. Okay, so using 2 and 3, so L11 is square root of A11 and A11 is 1. Okay, now I can compute from here because I have the I is equal to 1 I is known to me. Okay, so I'm going to compute L21 from here. So if I use 3, I can compute L21. And what it is going to be? So we have A21 minus, if you notice this summation, this is from k is equal to 1 to j minus 1, right? And j is 1 here. So basically this summation is not contributing. So I simply have A21 divided by L11. So this is simply 2 divided by 1, which is 2. Okay. And now if I can also compute the L31 from here, because if I take j is equal to 1, so this summation is not going to contribute. So L31 is going to be A31 divided by L11. So A31 is 3. So basically we have found the first column of the lower triangular matrix L. Okay. Now you can compute the L22, and then L22 you can use to compute the rest of the two entries. So likewise, using 2, we can compute L22. So this is going to be A22 minus, now I is 2. So this is going to be L21 square. And L21 is already known. So A22 is 2 and L21 is 2. So this is going to be L21 is 2 and A22 is what? 8. Sorry. So this is 2. Likewise, you can compute L32. So L32 is going to be A32 minus this summation. So this is A32 minus summation k equals 1 to j minus 1. J is 2, so this is 1 to 1. and L ik ljk. So I will have here L3k L2k divided by L22. Okay, so this is simply A32 minus L31 times L21 divided by L22. And I've already computed L31 and L21. So this is, you can simplify this. So A32 is 22 minus, okay, this you can simplify and find it. What is the output of this entry? Okay, and likewise you can find L33. So this is going to be, you use 2. So A33 minus, we will have summation Lik. K is running from 1 to 2. So this is going to be L31 square minus L32 square root of this. Okay, and you can find this entry as well. So once you have found this, you actually have computed the matrix L, and A is having this representation L into L transpose. Okay, so is it clear? Okay, so I'll just close it by discussing one last thing, that if you recall that when we were having the discussing this LU decomposition of the matrix A, I remarked it that this decomposition is not unique. That is, you take any diagonal matrix, then you can form the new decomposition of the matrix A by this L tilde and U tilde, where L tilde is nothing but L times D inverse and U tilde is D times U, right? So this decomposition was not unique. But if we talk about the Cholesky decomposition, we can prove that, suppose you have A is equal to L into L transpose, and suppose we have another decomposition, M into M transpose, right? Then we can prove that M is some diagonal matrix, so L times some diagonal matrix D, where D is such that right, that is D is a diagonal matrix with plus minus 1 in the diagonal entries. So what does this say? That the Cholesky decomposition, it just differs by the, suppose you have a 2 Cholesky decomposition, they will just differ by the sign in their columns. Okay, so I think it's a short proof. So let me just discuss that. So we have L is equal to L transpose, and this is the same as M into M transpose, where M and L, they are the lower triangular matrices. Okay, so note that from here, I can write it down that M into M transpose, and let me take the L that side. So since A is, you can conclude from that A is positive, definite, and symmetric. So these matrices L and L transpose, they're going to have the non-zero determinant. That is, they're going to be invertible. Okay, so I can simply write it down as L inverse, and this side I will get it as transpose of inverse of the L transpose. Okay, and this equals identity. And now let me club this here. So this is L inverse M, and this is going to be L inverse M transpose. So this is equal to identity. Okay, So this is some matrix, right? And this is a transpose of that matrix. So we are getting that this is equal to identity. This means that L inverse M is nothing but the inverse of this transpose, right? So what can you say about, okay, so if M is lower triangular and L is lower triangular, what is going to be the structure of this matrix? If L is lower triangular, L inverse is also going to be lower triangular. Okay, so this is also a lower this is going to be a lower triangular matrix. Now this side, so it's like L inverse M inverse and then the transpose of that, right? So L inverse M is a lower triangular matrix. Its inverse again is a lower triangular matrix. And what is going to be the transpose of that?
Upper triangle.
It's going to be an upper triangular matrix this side. And what this relation is implying that the lower triangular matrix is the same as the upper triangular matrix.
Diagonal.
So this means that this L inverse M, this is going to be a diagonal matrix because this is only possible when you have L inverse M as a diagonal matrix. So this implies that the matrix L inverse M, which we are calling it D, this is both lower and upper triangular matrix. This implies, hence, this is just a diagonal matrix. Okay. Now we have got that this is a diagonal matrix. Now let's try to get more information about what are the entries of this diagonal matrix. So let's look at this relation. So let's call it as 1. So from 1, so L inverse M is D. Okay. And here L inverse M transpose. L inverse M is D. So D transpose is again D. Okay. So we are having that D square is equal to I. Okay. So D is a diagonal matrix whose diagonal elements squared is nothing but 1. Right. So this means that the elements of D can be either +1 or the -1. Right. So this implies D is a diagonal matrix with +-1 as diagonal entries. Right? And we have got this relation that L inverse M is D or M is nothing but L times of D. Okay, so if you have two different Cholesky factorization of the matrix A, the only possibility is that you can have the multiplication to the columns by -1. That's the only difference you can have. Okay, otherwise they will be same. All right, so I think this is all, and since it is the time, so there's one thing which I really did not discuss in detail is the operation count. Okay, so this you can try to do, you can just take it as a reading project and try to do yourself. So what I mean by the operation count, so for example, if we talk about the Gauss elimination, right? So how many total number of operations are being done to solve the system Ax is equal to B? Okay, so A is an n by n matrix and X is a vector of size n and B is also a vector of size n. So finally, when you solve this, you obtain the solution using the any of the method. So what is the total number of operations performed. So that is basically the operation count. So just to give a glimpse that, for example, Gauss elimination. So just in the first step, if you try to observe, so you find the multipliers Mij's, right? So for finding the Mij's, you basically divide Aij by Aii, right? So basically you have to count how many divisions are done. So total number of multipliers, if you look at when we are finding for the x1 variable, there will be n minus 1. Okay, so you are requiring n minus 1 division. Then you are multiplying these multipliers to each of the row and then eliminating the variable. So how many divisions are required, how many multiplications are required, how many total additions are required. So that if you total number of counts you do, so that is called the operation count. And for the Gauss elimination, which I have mentioned, that this is of order n cube. Okay, even for the LU decomposition, so for Gauss elimination, it is of order n cube. For LU decomposition as well, this is of order n cube. So when I say order n cube, this is like constant multiple of n cube. Now that constant differs. So though they are of order n cube, but the constant which you will have here is different than the constant which you will have here. Okay. And in fact, I've mentioned that Gauss Jordan also have order n cube. Cholesky also have order n cube, but the constant are different. So for example, in Gauss Jordan, here it is n cube divided by 3. In the Gauss Jordan, it is n cube divided by 2. Okay, so this is how, but these direct methods are of order n cube. They take the operation count is of order n cube. But in the iterative methods, it is of order n square. Okay, so that is why the iterative methods are more useful when you have n to be very large, because n cube and n square gets a huge difference, and it really affects the computational time. So you imagine that you're implementing this algorithm in the computer, and if it is taking n cube time, and say n is of order 1 lakh or even more than that, so n cube is going to be very large as compared to the n square. Okay, and when the operation counts are large, this means that it is going to take more time to solve the system. Okay, and when you try to design the efficient algorithm, this means that you want to minimize time as well. So time is a big factor in solving the systems. So yeah, I think with this, I'll conclude here. So this is the last lecture of this course. If you have any doubts, you can ask now, and then we will end this meeting.